In this video, I'll talk about some and prove some recognizable properties of graphs. So I mentioned this in the previous video, but here I'll define exactly what is meant by a recognizable property. We call a property, a graphical property, recognizable, or a parameter recognizable, if for each graph G of order at least 3, it's possible to determine the value of the parameter or whether G has the property by looking at the subgraphs G minus V for each vertex in the vertex set. So that is just by looking at the vertex deleted subgraphs, all of the vertex deleted subgraphs of a graph, we can either determine the value of the parameter or whether G has the property or not. So that's what's meant by a recognizable property. So we'll start with perhaps the most basic of these and possibly the most useful for our purposes, and that is that the order, size, and list of degrees of the vertices of a graph are all recognizable. All right, so let's go ahead and prove this. So what do we have to prove here? We have to prove, given the vertex deleted subgraphs, we have to show how to determine the order, the size, and the degrees of the vertices. So let G sub I be equal to G minus V sub I. So here, I guess in the background, maybe I should have began the proof of this, but whatever, in the background here, I'm going to let G be the graph, be a graph, and let's say its vertex set is V sub 1, V sub 2, up through V sub n. And so, all right, so I'm going to let G sub I be G minus Vi for each I between 1 and n. Now, first off, we can recognize the order of G just by noting how many vertex deleted subgraphs there are. So the order of G is the number of vertex deleted subgraphs. Also, we could also recognize this by looking at the order of any G sub I. Also, the order of G is the order of G sub I, plus 1 for any I, right? Because it's a vertex deleted subgraph. Okay, I'm also going to let M sub I be the size of each G sub I for each I. So, okay, order is easy to determine. What about the size? So let M sub I be the size of G sub I for each I. And then let's consider just any edge of G. So let E, and let's just say it's V sub I, V sub J. Where we don't want to run into problems. We'll call it V sub J, V sub K. Let E equal V sub J, V sub K be any edge. Then think about which vertex deleted subgraphs E must be present in. Well, if I delete, it's not going to be in G sub J because I'll have deleted V sub J. It's not going to be in G sub K because I'll have deleted V sub K, but it will be in every other vertex deleted subgraph. Then E appears in every vertex deleted subgraph G sub I with I not equal to J or K. Right, as long as I is not equal to J or K, E will appear in there. So E appears in n minus 2 vertex deleted subgraphs. And E was an arbitrary edge, so this is true for every edge of the graph. Each edge appears in exactly n minus 2 vertex deleted subgraphs. So if I sum up the m sub i's, so sum of the m sub i's, what do I get? I won't get, so this is I equal 1 to n, all of the vertex deleted subgraphs. I won't get n times m, but rather n minus 2 times m, because I will have counted every edge exactly n minus 2 times by summing up all the m sub i's. So what does this mean? This means that m, the size of my graph, is exactly the sum of the m sub i's divided by n minus 2. So that's how we can recognize the size of G. All right, finally, the list of degrees. So now we can determine, the degree of V sub I by noting that the degree of V sub I, so if I look at G sub I, the vertex deleted subgraph where I've removed V sub I, well, that will have m sub I edges in it, but I know there are m edges total in the graph, so the leftover edges, the difference of m and m sub I, must be all of the edges incident with V sub I. So the degree of V sub I is m minus m sub I for each I. And so that proves that these are all recognizable properties. So one consequence of this is that regularity is going to be a recognizable property. I'll mention that in a second. Okay. So order, size, and degrees of each vertex, these are all recognizable. So this is very helpful in determining a solution to a set of vertex deleted subgraphs. So this is one of the problems that comes from this reconstruction problem is given a list of vertex deleted subgraphs or deck of vertex deleted subgraphs, can we determine the solutions or the possible graphs that have these as the vertex deleted subgraphs? Of course, if the reconstruction conjecture is true, that means there's only one graph that has these as its vertex deleted subgraphs. So let's see if we can do this. So we'll illustrate the previous theorem and determine the graph here. All right. So we can recognize the order, size, and degrees of each vertex. So order, well, that'll be 6 because 1, I have 6 vertex deleted subgraphs, and 2, each vertex deleted subgraph has 5 vertices in it. The size will be 6 minus 2, so 1/4 of the sum of the m sub i's. So let's do that. Let's add that up. So this one has 1, 2, 3, 4, 5, 6, 7. 1, 2. So that looks like 14 from those two. 2 times 7. These two are also the same, and there are 6 edges in each of those, so 12 from those two. And then down here, these are each the same, 3, 4, 5, 5 from each of those, so plus 10. That's 26, that's 36, divided by 4 is 9. So the size of the graph is 9. And now that we have the size of the graph, now that we've determined that, now we can determine the degrees of each vertex. So degree of V1, well, G1 has 7 edges in it, so there's 2 remaining edges, so the degree of V1 is 2, and that's the same as degree of V2, since those are isomorphic graphs. Degree of V2, there were 6 edges in each of those, so degree of V2 and degree of V3, and degree of V4 are both 3. And finally, degree of V5 is 4, along with the degree of V6. All right, so this is some good information that we can add to our arsenal. Can we now determine G from this? So one, we've recognized these properties. Can we now determine G? So one way I like to do this is I'll start with my vertices of lowest degree, or consequently, or on the other hand, or a highest degree if that highest degree is close to the order of the graph. So like if I had a vertex of degree 5, for instance, I might start there. Right, so actually I might start here. Maybe I'll start with this vertex degree of V5 is 4 and degree of V6 is 4. Because that means if the order is 6, right, the highest degree is 5, it means there's only one vertex. So that is, take G5 and G6, and we need to add a vertex into this of degree 4. So that is, there's only one vertex left out from this. And it needs to be such that when I remove any vertex, I'll end up with one of these. So in particular, look at G5 and G6, the symmetry there. Let's see. All right, so we got to think about it for a second. Feel free to pause the video if you want and try and figure this out yourself before I give it away. And in fact, I am going to pause the video myself and think about it for a second. All right, so there's some things that we can deduce here. So think about, we know the degrees of the vertices of G. We have 2 vertices of degree 2, 2 vertices of degree 3, and 2 vertices of degree 4. Here in G5 and G6, I have a vertex of degree 1. And so that means this new vertex I add in, it has to be adjacent to that vertex. So there's one thing I can say for sure. And then what, I have 2 vertices of degree 2, or I have 3 vertices of degree 2 right now, and 1 vertex of degree 3. Okay, so let's see. This needs to be adjacent to 3 other vertices here. So if it were adjacent to this one and this one, then that would mean I would end up with, that'd be 2 vertices of degree 3. That would be okay. So what if it was adjacent to this one, and this one? That would give us 2 vertices of degree 2, 2 vertices of degree 4, and 2 vertices of degree 3. Okay, so maybe this is it. Maybe this works. So this would be V sub, we're saying this would be V sub 5. And now what we can work on is, can we identify what V sub 6 would be from this? So V sub 6 is my other vertex of degree 4. That would be this one. So what does my graph look like? This would be V sub 6. So what would G6 then look like if this was G5? So again, we can do some trial and error. Again, maybe you've come up with a better way to think about this than I have, and that's great if you can do that. So if I remove V sub 6, then what, I'll have V sub 5 attached to this triangle. And then it looks like I would have, so coming off of V sub 5, I'd have just a path of length 2 coming off of it. That is G sub 6. Okay, so that checks out. So that would be my V sub 6. How about my G sub 3 and my G sub 4? So again, we're testing this hypothesis out. This is really G. So V sub 3 and V sub 4, these are my vertices of degree 3. So that would be these two. So maybe V sub 3 is this and V sub 4 is that. And what happens if I remove, say, V sub 3? Then G3 would be the graph. So I'd remove that. What would I have here? I would have, looks like I'd have this, I need some more room. G sub 3. I would have this triangle. I'd have V sub 5 adjacent to those two, and then I would still have this. I would have V sub 6 coming down here to that one, and then back to V sub 5. Right, is that right? And that doesn't quite look right, does it? So let me double check that I really computed that right. I removed V sub 3. I'd be left with V sub 4, V sub 5, V sub 6. Those would form a triangle. And then I'd have this 4 cycle between V5 and V6. So that is not quite what we see here. So that's not gonna work. All right, back to the drawing board. Yeah, that didn't quite work out. All right, so sometimes it's good to see the problem solving process like this. So let's see. So back to the drawing board. If you're sick of seeing me, if you've already figured this out, you're sick of seeing it, feel free to skip ahead. That's okay. So again, we're adding in V sub 5. And what did I try? So I know that's adjacent to this one. And then what did I try last time? I tried this one adjacent to both of those and then to that one. So yeah, why didn't that quite work out? That would have given me the right degrees, but the structures weren't right. So I guess one other thing we could try here would be, right, we have to leave off one vertex. So last time I left off this vertex. And I know, let's see, I can't leave off this vertex. If I leave off this vertex from being adjacent to this, this would be adjacent here, here, and here. So that would be degree 3, degree 3, degree 3, and we don't have that in the graph. So can't leave off this vertex. That means I have to have this, right? This has to be adjacent there. And so I need to pick 2 of these. So, right, so now it must be, well, if my logic is right, it must be this graph. So this would be my V sub 5. This would be my V sub 6. This would be, let's say, V sub 3, V sub 4, and V sub 1, and V sub 2. So let's check V sub 6. So yeah, we'll just go one by one. So let's do G1. What would G1 look like? So I'd remove that. Yeah, I don't know if you can tell, but if I remove G1, I'll be left with this graph, which is isomorphic to G sub 1 and G sub 2, right? Just sort of reflect it. And so that, yeah, that works for G sub 1, G sub 2. Let's try that. If I remove G sub 2, yeah, again, we're left with that same graph. So quick mental computation there. And this would actually be, the way I'm envisioning it, it would be exactly this one. Yep. G sub 3. Take a look at G sub 3. G sub 3, I'd have this dongle coming off of here. Yeah. So G sub 3, I'd have this vertex up here would be V1, be adjacent to V5, and then I have this triangle between V5, V4, and V6. All right, so that would be V5. Yeah, I guess we can do it like this, V4, V6, V2, and then V4 and V6 are adjacent. G minus 4, I'm going to speed things up a little bit. I'll just kind of do a mental check here. V sub 4. Yeah, now we'd end up with V2 and V6 would be this dongle. I'd have V2, V6, and the rest of this appears right. Yep, the rest of that would work. And then finally, I can check G sub 6 and just kind of do a mental check of that. Yeah, I'll end up with this path of length 2 attached to a triangle. And so this checks out. So this is my graph G. So maybe we can make it look a little bit nicer. I see a way to make this look nicer. My graph G is this one. And so that's sort of the process of determining a graph from its vertex deleted subgraphs is using these. Okay, I'm going to end this video here. In the next video, we'll take a look at some more recognizable properties.